Okay, so so last time we did order sets. Today we're going to talk about the main idea today is boundedness. Okay, so boundedness. Okay, and this is actually something that this is sort of like one of the main concerns of analysis. One thing that analysts like to do is to see if things are bounded or not. Okay, so see if you can get some sort of control over some sort of mathematical construct. Okay, so okay, and we can talk about boundedness now that we've talked about ordered sets. So so here's the definition of the first definition of boundedness. So suppose you have a subset of an ordered set. So this thing here is an ordered set. Okay. So you have a subset of an ordered set, and suppose that you have there's this thing, an element beta in S, and you know that beta is bigger than or equal to x for all x in E. Okay, so there's some element of S and it's bigger than or equal to everything in E. Okay, then we call this thing an upper bound of E. Okay, so that's sort of a simple idea. Then we call beta an upper bound of E, and we say that E is bounded above. Okay, this is pretty simple idea, right? Like if you're in the real numbers, you have some set, like the set the interval 0, 1. Well, then 2 is an upper bound, right? To every element. Suppose this is our set E. Then 2 is bigger than everything in E, and so we say that E is bounded above, and this is an upper bound. Okay, so pretty simple idea. Okay, and then similarly for lower bounds and bounded below. So I'm not going to write out that definition, but we can also talk about lower bounds and say that the set is bounded below. So this set is, of course, bounded below, and -1/2 would be a lower bound for it. Okay. Okay. More interesting and far more crucial is the following definition. So if in addition we have that for all upper bounds of E, for all other upper bounds gamma of E, we have that gamma, that beta is less than or equal to gamma. Then we call beta the least upper bound. Of E. Okay, also called the supremum. Sometimes you'll see this notation, supremum of E. This is what Rudin uses. Other books sometimes use love E, least upper bound of E. Okay. So this is the key thing. So suppose you have that is, so beta is an upper bound of E. Suppose you have an upper bound, but you also have, but the upper bound has this property that given any other upper bound, the other upper bounds are bigger than or equal to beta. That means that beta is the least of the upper bounds, right? And we call it the least upper bound. Okay. Okay. So like if we're over here, 2 is not the least upper bound, right? Because you can have some other 1.5 is an upper bound and it's less than 2. Okay. For this set here, the least, the value 1 is an upper bound and it's the least upper bound. Okay. So, right. So, everybody okay? Pretty straightforward, I think. Okay. So, okay. So, and this is going to lead to us answering the question, what does R have that Q doesn't have? Okay. Let's go back to, let's recall that in Q we had made these two sets. We let A be the rational numbers where the number is positive and the square of the number is less than 2, right? And we had this other set, which was the numbers are positive and the square is greater than 2, right? And what we saw was that this set has no greatest element, right? And this set has no least element, right? These, in the picture, there was this hole at the square root of 2, right? Because the square root of 2 doesn't exist in Q. And A was all the rational numbers here, and then B was all the rational numbers above 2, above the square root of 2. And we saw that you never have a greatest element of A, and you don't have a least element of B. Okay. So here's the funny thing. So B is actually the set of all upper bounds of A. Does that make sense? Okay. Everything in B is an upper bound of A, right? And these are all the upper bounds of A. Okay, these are all the upper bounds of A. But you notice something funny, that there is no least upper bound. Notice. There is no least upper bound. Right? This set, so A does have upper bounds, but there is no least upper bound in Q, right? So like whatever upper bound you take, there's always an upper bound smaller than it, right? Okay, so there is no least upper bound of B, and conversely, if you're thinking about lower bounds, there is no greatest lower bound of B, right? There's no least upper bound of A. There's no greatest lower bound of B. Okay. So that leads us to the this important idea of the least upper bound property. Okay. Okay. Did you've all read the book, I guess? So can anybody tell me what the least upper bound property tells you? Do you remember the least upper bound property? Okay. So this is actually the most important idea in the section, I'd say. Okay. Here it is. So have S an ordered set. Okay. Suppose the following is true. That for any non-empty set E in S, if E has an upper bound, then E has a least upper bound. Okay. In that case, we say that S has the least upper bound property. Okay. In that case, we say that S has the least upper bound property. Okay. So this is a statement about S. Okay, you've got S. Let me hold on. People are copying. Okay, so you've got S, an ordered set, and it has this property that whenever you have subsets that have upper bounds, the subsets always have a least upper bound. Okay, so what this example is over here is showing that Q fails to have that property, right? Q does not have the least upper bound property. It's an ordered set, but you can have a set that has upper bounds, but has no least upper bound, right? A has upper bounds, but there is no least upper bound of A, okay? That example shows you that Q doesn't have the least upper bound property. Okay, so, right. So Q with its regular ordering does not have the least upper bound property. Okay. And the punchline of the whole chapter is basically that R does. Okay. That what distinguishes the real numbers from the rational numbers. Because you think, what can you do in the real numbers that you can't do in the rational numbers? You can do almost everything, in the rational numbers, but you don't have this property. You don't have this property. And basically, R is constructed so that it has this property. Okay. So right now we're talking about least upper bound property. So right now we're not going to talk about R in particular, but we're just going to think about ordered sets that have the least upper bound property. Okay. So so here's our first theorem. You have S, an ordered set. The theorem is this, that if S has the least upper bound property, then it has the greatest, then S has the greatest lower bound property, greatest lower bound property. Okay, so, when you see the least upper bound property, you might think, why don't we talk about the greatest lower bound property, right? Are we prejudiced towards upper bounds? And in some sense, we are prejudiced towards upper bounds. People like upper bounds. I don't know. That's not true. Anyway, but when you see this sort of thing, you could think, well, what about a greatest lower bound property? Couldn't you also say that, wouldn't you also want to have the property that given any non-empty set with a lower bound, it's guaranteed to have a greatest lower bound, right? If you care about the existence of an upper bound, right? How come we don't talk about that? And the reason is that whenever you have the least upper bound property, you have the greatest lower bound property. So if an ordered set has this, this property, it's going to have this property, and vice versa. And vice versa. Yeah. Okay. So these are equivalent properties. Okay. So okay. So let's prove it. Okay. So let's prove it. Okay. So suppose that, and we're only going to prove the forward direction, because the backward direction, you just turn the argument upside down, basically. Okay. So suppose that S has the least upper bound property. Okay. And now we want to show that S has the greatest lower bound property, right? So what do we have to do to show that? We have to show that if we have a set that has a lower bound, then it has a greatest lower bound, right? So let B be some subset with, and B has to be non-empty, and say that and suppose B has a lower bound. Suppose that B has a lower bound. Whoops. B has a lower bound. Okay. We want to show that B has a greatest lower bound. Right. So greatest lower bound, which I forgot to mention, is called the infimum. The inf of B, or sometimes just glove of B. Okay, I keep on looking at you, Charlotte. I'm not sure why. I should look at everybody else. Sorry. Maybe because you're in the middle.
Probably.
Okay. Okay, so we want to show that B has a greatest lower bound, right? Okay. So, but all we know about our set is that it has the least upper bound property, right? So what we do is the following. We say, well, let L be the set of lower bounds of B, right? Let L be the set of lower bounds of B. And what we're going to do is apply the least upper bound property to L, right? We'll apply the least upper bound property to L, and that will give us, that will give us something that's, a least upper bound of L, right? So that'll be, and we're hoping that that will be the greatest lower bound, right? We're hoping that the least upper bound of the set of lower bounds will be the greatest lower bound of B. Make sense? So got some set B here, right? I'm drawing things as if they were on the real line. Sometimes you need to have some sort of picture. This picture, this is completely abstract, but anyway, sometimes it's useful to have a picture. So we have our set B. It has a lower bound, right? Right. We have our set B. It has a lower bound, and what our strategy, we want to find the greatest. We want the greatest lower bound of B, and our strategy will be to let L be the set of all lower bounds, right? So we've got all these lower bounds here, right? And we're going to consider the least upper bound of L. Okay. Hopefully that will be that will be the greatest lower bound of B, right? So that's the strategy, and it makes sense, right? It's a natural thing to do. Okay, so we want to apply the least upper bound property to L, right? Well, for us to apply the least upper bound property to L, what do we need to do? L has to be, right, so remember the least upper bound property. Least upper bound property says if you're a non-empty set and you have an upper bound, then you have a least upper bound. Okay, everybody all right? Julie, you okay?
Yeah.
Yeah, okay, right. So in order to apply the least upper bound property, we need to show, one, that this is not empty, and two, that it has an upper bound, right? So, so notice, one, L is non-empty, and two, L has an upper bound. Maybe I'll let you think about that. See if you can figure out. Why does it make sense to you that L is non-empty? that the set of lower bounds of B is non-empty, and that the set of lower bounds of B has an upper bound. Okay, I'll let you think about it for a minute. Okay, I'll just go walk around outside. So I often will just leave the class so that you guys can talk to each other without me feeling like I'm listening to you.
So it wants us to figure out why those two imply that B is similar.
Or I think like how we know that those two are true.
Supposing that B has a lower bound, which makes L not empty.
Okay, anybody have an idea? Why is L non-empty? Why is the set of lower bounds of B non-empty? How do we know that B has a lower bound?
Supposing
We said
that
so,
it does.
right? We said suppose B has lower bound. Okay, so that's by hypothesis, right? We know that, right? B has a lower bound. Okay, right? B has a lower bound. Okay, why does L have an upper bound? Why does L have an upper bound? How do we know that L has an upper bound? Here's L. Yeah.
Is it just because B has the greatest lower bound?
Well, that's what we're hoping for. We don't know that yet. Yeah, but it does have to do with B, right? Take any element of B, right? Any element of B, all these guys are lower bounds of B. That means that any element of B must be bigger than all of them, right? So any element of B will do as an upper bound of L. So why? Because any element of B for any element B and B, we know that if L is the lower bound, then B is greater than or equal to L. Right. Right. You take any because L is a lower bound of B. Right? Is that okay? Okay. So, yeah. So the set of lower bounds of B is non-empty and has an upper bound, and so by the least upper bound property, right? Since S has the least upper bound property, we know that L has a least upper bound. Okay. Everybody all right? Yes, Charlotte.
Okay, so in the least upper bound property,
Yeah.
there was the part that said that for any non-empty E that's a subset of S.
Yes.
I guess I like two-ish questions, but like first, like what's the relevancy of it being a subset, and why do we not have to prove that L is also a subset of S?
Oh, well, I mean, when we say S, the second question, regarding the second question, S is our world, basically.
Okay.
Right? So when we're talking about the set of lower bounds of B, we're not talking about within some other, right? S, that is within S. So we don't have to say that it's a subset of S, because we're only talking about this world of S. Okay. So you might think like, suppose we're talking about Q, and Q sits inside of R, And are we, when we say the lower bounds of, if our S were Q, say, so maybe this is how you're thinking, I'm not sure. Maybe you're thinking, well, what if S is actually sitting inside of a set and there are other lower bounds here, and so we have to say that it's inside of S. Maybe that's what you're thinking?
Kind of.
Yeah, so you don't have to, because when we say, you know, we're sort of restricting ourselves to the world of S when we make this statement at the beginning. Yeah, but we could. No, we shouldn't. We shouldn't. Sorry, we shouldn't. Yeah. Yeah, that's just assumed, basically. Okay. And then the other question was, why do we have to talk about subsets of S? That's just the nature of the least upper bound property. The least upper bound property is about subsets of S, right? So least upper bound property is, you know, whenever you have a subset of S that has an upper bound, then it has a least upper bound, right? It's just this sort of like global property that holds for any subsets. Okay? Any subsets of S that satisfy this condition, you know, have this conclusion. Does that make sense?
Yeah.
Okay. Any other questions? Okay. Yeah, please feel free to, you know, it's only 5 students, you know, you should feel free to just, you know, we can take this at whatever pace you like. Everybody close your eyes. Raise a finger if we should go faster. Raise a finger if we should go slower. Oops. Raise a finger if we should go faster. There's some twitching. Okay. Raise a finger if we should go slower. Okay. Okay, everybody open your eyes, thank you. Okay. Okay, great. So, so I'm going to go slightly faster then, but not too much faster. Okay. So, what have we done? We said that there is a least upper bound, right? So we know that this least upper bound exists. Okay, and we're hoping that that guy is the greatest lower bound of B, right? So that was our strategy. So let's claim it. Let's say we claim the least upper bound of L is actually the greatest lower bound of B. Okay, right. So we need to show 2 things. One, that least upper bound of L is a lower bound of B, right? And 2, that the least upper bound of L is the greatest lower bound. Right? Because that's what being the greatest lower bound means, right? Right? That it's bigger than all other lower bounds. Okay. Okay. So the second part is actually, what do you think? Is the second part harder or easier than the first part? We want to show that the least upper bound of L is the greatest of the lower bounds. L is the lower bounds. Right? L is the lower bounds. This thing is the upper bound of the lower bounds. Right? This thing is the least upper bound of the lower bounds. Right? So what does that tell you? It's going to be bigger than all of the lower bounds, bigger than or equal to all the lower bounds. So this part is actually trivial. This part is straightforward. Right? So 2 is easy. 2 is easy. Right? The least upper bound of L is an upper bound of L. Right? Right? L, the set of lower bounds of B. The lower bounds of B. Right? Since it's an upper bound of these guys, it's bigger than or equal to all of them. Right? So given any other lower bound in L, right, we know that this thing is going to be bigger than or equal to it, right? So it's definitely it's definitely greater than all these guys. Okay. What we don't know is if it is actually a lower bound at all. Okay, that's the hard part, or the harder part. So if we knew that this thing were actually a lower bound, we'd be done, right? Because as we just said, it's bigger than or equal to everybody else, so it would be the greatest lower bound. Okay, so the only thing we need to do is show one that this thing is actually a lower bound. Okay, so so it suffices to show that this thing is a lower bound of B. Sorry. Okay. Okay. So yeah. So well, we saw that. You know, if B is an element of B, then B is greater than or equal to L, right? For all L and L, right? That's what we saw right here, right? So what does that say? That says that that if you're in B, then B is an upper bound of L, right? B is an upper bound of L. Right? But this thing here, right, we're trying to show that this is a lower bound of B, right? We're trying to show that this thing is a lower bound of B. Well, this is the least upper bound of L, and B is an upper bound of L, right? So we know that least upper bound of L is less than or equal to B, right? Because B is an upper bound of L, so this is going to be less than or equal to B, less than or equal to that guy, right? So what does that tell you? That for any element of B, this thing is less than or equal to B, right? In other words, this thing is a lower bound. So this is a lower bound of B. Okay. So that's the end. Okay. Right. So remember what we did. You know, we wanted to show that the least upper bound of the set of lower bounds was actually the greatest lower bound of B, right? And so what we did was we showed that this thing actually is a lower bound of B, right? Because whenever you have anybody in B, that's an upper bound of L, and this is the least upper bound of L. So it's going to be less than or equal to that. So this thing is less than or equal to anybody in B. So this is a lower bound of B. Okay, and then we made the sort of obvious observation that it's going to be the greatest of the lower bounds because it's an upper bound. It's because it's an upper bound of the lower bounds. Okay, so as long as you keep your sanity, it's easy. Yes, Anne?
In these two sets,
Yeah.
so the only element that they have in common is the least upper bound of L or the greatest lower bound of B. Like they have different elements except for that one that they have in common.
Which sets?
B and L,
B and L. Well,
because they both contain that one element.
So the greatest lower bound of it need not be contained in the set. So like if you're thinking about, suppose we're looking at something like this, 0, 1. Suppose that's our B. Okay. Then the greatest lower bound is actually 0, but 0 is not in the set. So it's not a common element. Yeah, it's just sort of like the borderline element. Yeah. Okay. So maybe this will require a little bit of extra thought, but yeah, just it's more like you have to chase through. This is more like what we call a definition chasing theorem, more than a sort of intuitive theorem. So just don't worry. If it seems confusing, don't worry. Just go home and think about it a bit. Okay. So, yeah. But I think it's useful to keep this kind of picture in mind. Right, that will give you some idea of the strategy. Yeah. Okay. Okay. So now we're going to move on to another topic, which is the idea of a field. Okay. Have anybody seen this term before? Field? Some of you. Okay. So these are sort of very special sets. They're generalizations of like the rational numbers, the real numbers, the complex numbers, etc. These are all fields. Okay. So these things, what they have is they have multiplication. They've got division. They've got addition and subtraction and these sorts of things. And so a field is more like an abstraction of these ideas, right? Z is not a field because you can't do division. You can't do division within Z, right? Z is something called a ring, for those of you who've seen this term before, right? Okay, so like more limited idea. Okay, so okay, so we're basically just going to take these things and then abstractify them. When I first took a linear algebra class, when I first got to college, the very first definition was that of a field, and we did linear algebra over fields in general. That is, we didn't do linear algebra with real numbers or anything. We just did it over fields. Which is kind of crazy, but that's how we did it. Okay, so let F be a set with two binary operations, dot and plus. So these are generalizations of multiplication, multiplication and addition. They may not be what you think they are, such that. And then there are a bunch of axioms that it has to satisfy. So first is that x and y in F implies that their sum is in F. So this is what we call closure. X plus y equals y plus x for all x and y. So the addition is commutative. X plus y plus z equals x plus y plus z, right? For all x plus y, x, y, and z in F. So you've got associativity. And then there exists an element called 0, such that for all x in F, 0 plus x equals x, right? So there's something called an additive identity. And then for all x in F, there exists something called negative x, such that x plus negative x equals the 0 element. So there's additive inverses. Okay, so all these things, should hold. Okay. And similarly for multiplication, you've got analogous axioms, right? You've got there will be closure, there will be commutativity, there will be associativity, there will be a multiplicative identity. So there will be some number called 1 such that 1 times x equals x for all x, right? And then there will be multiplicative inverses. So inverses for all x in f that are not equal to 0. Okay, so I don't know if you've seen this mark, but it means excluding. So for everybody in f excluding 0, there exists an inverse element such that x times x inverse equals 1. I guess Rudin is writing it as 1 over x, so let's write it that way. Okay, and then the last thing is distributivity, that the multiplication and addition work well together, right? That x times y plus z equals xy plus xz. Okay, so what's a field? A field is just something that has a plus and a multiplication that behave as you would like them to behave as they do in your standard as in R. Yes.
Which axiom does do integers break?
Which axiom does integer? Which axioms?
I'm trying to think about it.
So let's see. Closure and addition, okay. Commutativity, okay. Dissociativity, okay. There's a 0, additive identity, okay. There's negative numbers, the negative inverse, additive inverses, okay. Right? Multiplication, closed, yes. Commutativity, yes, yes. Multiplicative identity, there's a 1, you can multiply by 1. Inverses. Is there always some number where you can multiply and get to the multiplicative identity for the integers, right? So like 2 times what? You would need a 1 over 2, right? You would need some sort of multiplicative inverse, and you don't. Okay, see that's where you fail. Okay. 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 So yeah. Okay, so fields. Okay, and the real numbers, if you want an example, so the standard examples are these here. Other examples are z mod p z, where p is a prime. Maybe I'll explain this next time, but there are things like this. It's when you take the integers 0, 1 to p minus 1. So like if we were looking at z mod 5z, that would be the integers 0, 1, 2, 3, 4. And then you would define addition and multiplication mod 5. So like 2 plus 4 would be 1. Right? 2 plus 4, you do it on a clock basically. Right? So like you do it on a clock. Right? So 2 plus 4 would be 1, right? 2 times 4 would be 8, but you have to do mod 5, so you come back to 3, right? Et cetera, et cetera. And it turns out if this is a prime number, then what you get is a field. But if it's not a prime number, then you run into problems. So like if it were z mod 4z, then you'd have a problem because then 2 times 2 would be 4, which mod 4 would be 0. So you'd have 0 divisors. And that actually turns out to be forbidden in a field. That actually won't happen in a field. You won't have 0 divisors in a field. So these are sort of the standard examples. This is sort of slightly more esoteric example. Okay. So there are a bunch of So these are like the basic axioms of fields, what are called the field axioms. And they're probably familiar to you from childhood, right? I think those of you who've been through the Common Core probably saw the commutative property, the associative property all the time. Right? Why was there such an emphasis on it? It's because these are the field axioms, and they're sort of like the fundamental properties of fields from which other more sophisticated properties follow. So like, there are other things that you might think are fundamental properties of numbers. For example, if you have x plus y equals x plus z, then y equals z, right? Or if you have x plus y equals x, then y must be negative x, must be I'm sorry, x plus y equals x, then y equals 0, excuse me. If you have x plus y equals 0, then y must be the inverse of x. And negative, the inverse of the inverse, the additive inverse of the additive inverse is the original thing. Other properties that are probably seem very fundamental to you are, for example, that 0x equals 0, right? Or that if x and y are non-zero, then xy cannot be 0. Or that negative x times y equals negative xy equals x times negative y. Or that the product of the additive inverses is just the product of the original things. Okay, so these are all like things that, you might be wondering why we didn't put these in the field axioms, right? Why didn't we say that 0 times any number has to be 0? The point is that all these things follow from the field axioms. Okay, all these things are immediate consequences of the field axioms, so we don't have to prove them. Yeah. So maybe next time we'll start off. It's not the most exciting thing. In fact, it's boring. But maybe next time we'll start off by seeing just like how some of these properties follow from the field axioms. Okay, and then we'll go on from there. And so, what's happening in this? What we're in the grand arc of the course, in the grand arc of the first chapter, what we're heading towards is the real numbers. Okay, and so what Rudin is doing is basically introducing step by step things that characterize the real numbers. So we started with ordered sets. The real numbers are an ordered set. We get to this, least upper bound property. The real numbers are going to have that least upper bound property. Now we're talking about fields. The next thing we're going to talk about is putting those two ideas together: order plus field. They have these things called ordered fields. Okay, and it's a little bit subtle. And then we'll talk about the real numbers. Okay. So next time we'll probably finish that up, and then go on from there. Okay. Okay, that's it for today.